Okay, here is another example. Which is the so-called slider crank mechanism. Okay, so what is the slider crank mechanism? We have one rigid body rotating about this point O, and let's call this point A, and we have another rigid body connected to OA, and the other end of the rigid body slides along this horizontal slot. Okay, so we're going to call this point B, and let's say OA is 1 meter, AB is 1 meter, and everything O and B are along the same horizontal surface, let's say. So this thing can slide back and forth like this. And let's say the angular velocity of OA is given, and the angular acceleration of OA is given. And let's say this is theta, and given theta equals 45 degrees for convenience. Okay, so let's say what we are given is omega equals 1 radian per second, alpha equals 2 radian per second, both anti-clockwise. So you're given something about the angular velocity and angular acceleration of this this part of the mechanism, and you're asked determine the velocity of point B, the angular velocity of bar AB. Okay, so this is not A with respect to B, it's the angular velocity of AB, and similarly angular acceleration of the bar AB. Okay, so these are things we want to determine. I mean, we could also determine acceleration of point B. Okay, so these are all things we can determine. So how do we determine this? So let's do the velocity first. So really the only thing to do is to use the two equations that we have, the velocity equation and the acceleration equation. Okay, before we actually get into the problem, let's talk about this mechanism for a moment. This mechanism is perhaps one of the most common kinematic mechanisms ever. This is pretty much in every traditional internal combustion engine car. Maybe it's not an electric car, but it's in pretty much every other type of car that runs on our road. So it's one of the most common mechanisms. There's billions of these guys in the world. Okay, so it's called a slider crank mechanism. This is the slider, this is the crank, and as the crank rotates, the slider goes back and forth. Or alternatively, as the slider goes back and forth, the crank rotates. In an internal combustion engine, the combustion of the fuel drives the crank slider back and forth, and that rotates the crank, that eventually rotates the wheel. So that's why this mechanism is used. Okay, so what we have been given are the angular velocity and the angular acceleration of this part of the mechanism, and what we are asked to find is the angular velocity of this mechanism as well as perhaps the velocity of this point and so on. So how do we do that? The only recourse is to use the two equations that we have, the velocity equation and the acceleration equation. To do these two things, namely velocity of point B and the angular velocity of AB, we only need to use the velocity equation. Okay, so what can we use the velocity equation for? We notice that OA is a rigid body. OA is a rigid body. This implies you can write this equation VA equals VO plus omega OA cross RA with respect to O, okay, where omega OA is basically our omega given K, or 1 times K. What is RA with respect to O? That's basically 1 cosine theta, 1 sine theta, okay? So 1 cosine theta I plus 1 sine theta J. So we know these two things. What is V sub O? V sub O equals 0. This implies we know what the velocity of point A is. We can just go 0. We can use this equation here, plug all these things in. 0 plus 1k crossed with again, it's 45 degrees. Cosine theta is 1 over square root of 2. So we have something like this. And that gives us 1 over square root of 2 k cross I plus k cross j. 1 over square root of 2, k cross I is j, k cross j is minus I. Okay, that's actually exactly the same velocity that we just saw for the disk. But in case, that's a velocity of point A, okay? Now, we were not really asked the velocity of point A, but that's all we can find using this equation. Okay, what about velocity of point B? Now, can we write VB equals, is the following equation true? So you take the velocity of point B and can we relate it directly to VO? Okay, so can we write VB equals VO plus omega cross R B with respect to O? Okay, can we write that? This is the mechanism. Okay, now we cannot write that. Not true, because B and O are not on the same rigid body. B and O are not on the same rigid body. Okay, so B, this point B is on this rigid body, O is on this rigid body, and they are on two different rigid bodies. So you cannot use that equation directly from O to B, but we can go from O to A, O and A are on the same rigid body, and then A to B, A and B are on the same rigid body. At least this point A is sort of common between this rigid body and this rigid body, so I can say A is common between these two rigid bodies. So what we can do is go VB equals VA plus omega AB, which is the angular velocity of this rigid body, crossed with RB with respect to A. Okay, so omega AB, the angular velocity of AB, is basically some scalar omega AB times K, and this is something we do not know. This is an unknown. Okay, so that's unknown. VA, we just found VA is 1 over square root of 2 j minus I. And what is RB with respect to A? This is the point B, this is the point A. So whenever you have a vector like this, you can always go OB minus OA. OB is basically 1 cosine theta plus 1 cosine theta. So that's 2 cosine theta I. And OA, This vector is something that we already wrote, which is I over square root of 2, j over square root of 2. So this is also 1 over square root of 2. So we have 2i over square root of 2 minus I over square root of 2 minus j over square root of 2. And that gives us I over square root of 2 minus j over square root of 2. Okay, so that's our b with respect to a. So we can plug all these things back into this equation, okay? So if we call this equation 1, 2, 3, 4, use 4, 3, 2 in 1. Okay, let's rewrite this equation. VB equals VA plus omega AB crossed with RB with respect to A. We've just established this VA to be equal to 1 over square root of 2 times the vector j minus vector I plus omega AB. What's omega AB is unknown. So let's say it's some scalar omega AB times the vector k. Omega is always in the k direction for our purposes, crossed with RB with respect to A, which is this thing. So I divided by square root of 2 minus j divided by square root of 2. Okay, so that's what we have. Let's expand this out a little bit. We still have 1 over square root of 2j minus I plus, let's bring the square root of 2 out. So we have omega AB divided by square root of 2. And we have k cross I. K cross I is j. And then k cross j is minus I. But minus of minus becomes plus. So it's plus j plus I. Okay, so we have this equation. We can simplify this ever so slightly by grouping together the I terms with each other and the j terms with each other. So if you just go I minus 1 over square root of 2 plus omega AB divided by square root of 2, and then the j terms are 1 over square root of 2 plus omega AB divided by square root of 2. That's equal to the velocity of B. Okay, so now that's weird because we've been asked to find the velocity of B and the velocity, angular velocity of AB. This is an equation that relates the two things, but it superficially feels like this is one equation and there are too many unknowns. Okay, omega AB, which is a scalar, then VB, which is a vector. Now, can we use this equation to solve for both VB and omega AB, which is what's asked? And it turns out you can, because the velocity of B is purely along I, which is essentially given by how this mechanism is constructed. So instead of saying VB is a general vector, you say, so this is one equation, and then we say VB equals VB I only along I direction. So we plug this into here, so we have VB I equals I times minus 1 over square root of 2 plus omega AB divided by square root of 2 plus j 1 over square root of 2 plus omega AB divided by square root of 2. Okay, now you just copy this equation out, except I've replaced the vector VB with the scalar VB times I. Okay, now we have one vector equation and two scalar unknowns, VB and omega AB. Now, if you have one vector equation like this, what you can do is equate the I component on the left-hand side with the I component on the right-hand side. Similarly, the j component on the left-hand side and the j component on the right-hand side. So if you say I components, we have VB equals minus 1 over square root of 2 plus omega AB divided by square root of 2. That's one equation. And then the j component equations is 0 because there is no j component here, equals the j component here is 1 over square root of 2 plus omega AB divided by square root of 2. Now this implies immediately that omega AB, like square root of 2 gets cancelled, omega AB equals minus 1 radians per second. Okay, we've solved this, and then we can plug this back in. We have VB equals minus 1 over square root of 2 plus omega AB divided by square root of 2 equals minus 1 over square root of 2 minus 1 over square root of 2 equals minus 2 over square root of 2 equals minus square root of 2 meters per second. Okay, so that's VB. Or the vector VB would basically be minus square root of 2I in meters per second. Okay, so we've now solved for the velocity of point B and the angular velocity omega of the bar AB. Okay, now which is exactly what was asked here, and that's it. So just to summarize what we did here, what did we do? We were given the angular velocity of this bar OA, and we used that angular velocity and this equation to go from the velocity, the known velocity of point O to get the velocity of A. This equation VA equals VO plus omega cross R A with respect to O, because O and A are on the same rigid body. And then we used the same kind of equation between B and O, and namely this equation, because B and A, not B and O, B and A are on the same rigid body, we can use that equation on the same rigid body, and essentially given the velocity of A, we can get the velocity of B and the angular velocity of AB. But we have to use one key equation, which is essentially the fact that B moved only horizontally. So that's a key equation that we needed to use before we could actually solve for everything. Now, if we wanted to get the acceleration of B and the angular acceleration of AB from the known angular acceleration of OA, which is alpha, so both these are for OA, then we need to follow exactly the same procedure, except the procedure involves using the acceleration equation instead of the velocity equation. You go through essentially exactly the same steps, but we use the acceleration equation. Okay, stop there.